This is a remote area of the South African Karoo Desert. Together with Australia's Western Desert, they're set to blossom with one of the most extraordinary creations of mankind. This transformation is an international collaboration to build the most powerful radio telescope the world has ever known, combining millions of receivers spread over 2 continents. It will push the boundaries of science into the dark ages of our universe, before the first stars were formed, and explore the birth of galaxies and the black holes at their heart, and look for the origins of life. Enlisting the universe's pulsars, it will chase ever-elusive gravity waves and sweep the sky to map cosmic magnetism. Achieving all this will give unprecedented challenges to industry, whose newfound knowledge will enhance their standing on the world stage. The combined collecting area of all the antennas gives this telescope its amazing sensitivity and its name. Manchester University's Radio Astronomy Observatory at Jodrell Bank in the north of England is the location for the Square Kilometre Array's international headquarters. Here, the multinational collaboration of astronomers, physicists, engineers, industrialists and policymakers is being coordinated as preparations are made for the construction phase of the project. The UK contribution is led by the Science and Technology Facilities Council and the universities of Oxford, Cambridge and Manchester, together with UK industry. 10 countries are participating in this truly global enterprise.
어떤 일로 오셨나요?
Why radio astronomy is so important is well illustrated by this optical view of the rather ordinary-looking Hercules A galaxy taken by the Hubble telescope. Viewed with the Very Large Array radio telescope in New Mexico, the galaxy looks rather different.
If you look at the sky with a radio telescope, you really don't see any stars at all. What you would see is lots of points of light in the sky, but actually most of those are giant black holes, at a large fraction of the distance to the edge of the universe, with matter pouring into them, and they are squirting out huge jets of matter which release radio waves. And they are actually the most common objects in the radio sky. And until people invented radio telescopes, we had no idea that these things even existed.
As well as certain phenomena generating radio waves, their other property is their ability to penetrate interstellar dust, to bring us images of the centre of galaxies. In the same way that when you drive a car through an underpass, the sunlight is obscured, but your car radio keeps working. Probing the dark ages before the first stars were formed is Professor Paul Alexander of Cambridge University. At the Cavendish Laboratories Radio Observatory, prototypes are being tested for the low-frequency aperture array to be deployed in Australia's Western Desert.
In the final telescope, there'll be somewhere close to 3 million of these deployed in Western Australia. And we form a telescope by not having any moving parts at all. We take these antennas and we take the signals from them and transmitted to what will be a central processor where the signals are digitized and then all brought together from all 3 million antennas. And what we're able to do is, by using digital signal processing, is to steer the telescope electronically to point at anywhere we like on the sky. And it will be an incredibly powerful instrument, and it will be the part of the instrument we use to look at the radiation that was coming from neutral hydrogen back at the very earliest times when the first galaxies and objects in the universe formed.
Hydrogen emissions from the far side of the universe have taken almost the entire age of the universe to reach us, and so bear a record of those earliest times. They can be identified because their spectral line frequency has been greatly lowered due to the Doppler effect.
Effectively, as you go from the top of the antenna
to the bottom of the antenna, you look back in time. The radio waves you're measuring at the top are more recent than the radio waves you measure from the bottom, which is quite a strange way of thinking about it, but that's what this piece of metal does for us.
In a way, it's like a geologist sort of digs down into the ground and you uncover deeper and deeper geological strata. You're looking back in the history of the Earth. With a telescope like SKA, when we look out farther into space, then we see farther back in time and we can uncover the past history of the universe and explain why the universe is the way it is today.
Professor Philip Diamond is the Director General of the SKA organisation, and he's particularly interested in the SKA's search for the origins of life in the universe.
We'll be looking for the signatures of heavy molecules, molecules that might carry the signatures of life, amino acids, things like that. And these will be very weak signals that the SKA will be the perfect instrument to detect. We'll be looking for evidence of these around newly formed planets.
It may even be able to detect what we call leakage radiation from extraterrestrial civilizations.
Involvement with industry is also vital for the success of this project, and knowledge exchange workshops are held worldwide. Chairing this STFC one at Jodrell Bank is Simon Berry.
We're talking about a project which is it's astronomy on an industrial scale, and again that's a big step from the kind of projects and facilities that we've had in the past, and it can only be really delivered with the help of industry.
Well, hopefully what industry will get out of it is they'll get it'll drive their own technological development. It's an ambitious or almost an audacious sort of project to be involved in.
The final challenge is the huge amount of computer power needed to process the data from the SKA's detectors, and the electricity required to supply them in such remote areas.
Currently, the amount of data which is produced on the entire internet in a year is around about 200 petabytes of data, which is a phenomenal amount of data. The square kilometre array is going to produce that amount of data in roughly a few weeks. Every few weeks.
One of the really interesting things about SKA is not things that we can predict we might discover, but what about the things we don't even know are there? So the unknown things that might be out there, that when you look at the sky with such a radically new and powerful instrument as the SKA, who knows what we might discover.